20 meters. So welcome. And tonight's topic, I'm going to go ahead and do this real quick. Tonight's topic is going to be tuned cables. So how many folks in here have ever cut a piece of coax and tuned it, whether it was a quarter wave or some other kind of phasing? I know a couple people have done it. So if you haven't done it, it's nothing to be afraid of. It's pretty easy. It just takes some basic math and a little bit of patience. Well, a whole lot of patience, to be honest, but we'll go ahead and get started. Let's see. I want this one. Okay. So you can tune a piece of coax, but you can't tune a fish. So we'll have fun with that this evening. So let's see. What's the whys and hows of tuned pieces of coax? So basically, what is a tuned piece of coax? A piece of coax cuts to a specific length to perform a specific duty within your system. Usually constructed of a coax and a couple connectors, and it can be terminated. With connectors, or sometimes it can be left open or shorted if need be for specific purposes. But it's critical that you know a few things with tuning a piece of coax, and one of them is the velocity factor. But when we talk about why would we need a piece of tuned coax, well, there's several reasons. You can use it as an impedance transformer. You can use it to control phase. You can use it for filtering, whether you want a notch filter or a bandpass filter. It can protect your equipment, and as a testing aid for a reference cable, or it can be used to improve station operations. So those are the main reasons we do that. Now, I typically use it for phase shifting for vertical arrays, but you can do broadside arrays with this, phasing it, and it's a very useful tool, especially the first three: the impedance transformer, the controlling of a phase shift, and filtering. Those are the primary three. The rest of them are kind of nice to do and have, but those first three are where we're going to concentrate what we're looking at here. Okay, so tuned piece of coax is an impedance transformer. So what you can do is, if you use a piece of quarter wave coax, when you cut it for a quarter wave, it inverts your impedance, right? So, or your voltage and your current. So you can take a high current location, make it a low current location, while raising the voltage at the other end. It's based on the formula where you have Z0, which is the impedance of the coax, is equal to the square root of Zn, which is your impedance that you're looking for, and Z load, which is the impedance of the system. So you see this a lot of times. People will have a 100 ohm load and they want to make it a 50 ohm load. And what they'll do is they'll take a piece of 75 ohm coax and cut it to a quarter wave electrically for that particular frequency. And what that does is, if you do the math, a 50 ohm load, and you're trying to match it to a 100 ohm load, when you do the square root of that, you end up with 70.7 ohms of impedance that you need to do that transformation. So 75 ohm coax RG6 will bring you right into that. Okay, does that make sense to everybody? And feel free, if you have questions, just to jump in. I have no problem with that. Coax cut to a half length electrically will repeat the impedance presented to it. So if you have a impedance that is, let's say, 50 ohms, and you want to make sure it's 50 ohms at the other end, you can insert a half wave piece of coax and it will be 50 ohms at the other end, right? That's why it makes an excellent feed line for an antenna with a 50 ohm characteristic impedance. So if you build something that's got a 50 ohm characteristic impedance, excuse my stumbling over that, you can use a half a wave at that particular frequency to provide you with an even match. Okay, so you'll get 50 in, 50 out. If you make it longer or shorter than a half wave, it doesn't guarantee your impedance is going to be exactly the same that you would have if you had a half wave on that. Tune coax for phase shifting. Okay, this is where I use coax the most for, or tune coax for my particular purposes. I build vertical phased arrays, 2 elements and 3 elements. And so I use different lengths. Typically for what I'm doing, I do what's called a Chrisman method for 2 element verticals, which means I have to phase shift 2 antennas. So I have one antenna I need to feed at 84 degrees and have another antenna I have to feed at 151 degrees. So in order to switch them back and forth, I put 284 lines in and 171 line in. What that does, it helps with the impedance, evening out the impedance between the 2 antennas, but it also splits the voltage equally among the antennas, so I get good signal to both of them. Okay. The other place you see a lot of times with phased cables or tuned cables for phase shifting is in stacked verticals. So I've got a picture here of stacked verticals. And what you have is you have a match that allows you to use those all at one time, or you can use one in one direction and one in another direction for diversity. But you need to have tuned cables for that. Okay. And then you can use it to build an array pattern. Okay. So if I had 2 verticals and I wanted a broadside array, I could put a 180-degree phasing line between the 2 verticals, and that would give me a figure-8 pattern off those 2 verticals. So it would null down the axis of the antennas, but produce 2 really narrow, tight lobes off both sides of the antenna, off the broad side of that antenna. So instead of an egg shape, you get a very nice peanut shaped, very narrow, and some gain off of those. So, you can do a lot of different things. 90 degrees between 2 verticals that are quarter wave apart will produce a cardioid pattern, like a heart shaped pattern in one direction or the other, depending on where you have that 90 degrees set up. So, and we're going to take a look at building a tuned cable tonight, so you'll get a little bit of a better feel for this. And then you can use tuned cables for filtering. Okay, when I say filtering, what do I mean? I mean, you could build a notch filter with it, or you can build a bandpass filter for it, or you can build a trap for it. So basically a quarter wave at a frequency, and it's a specific frequency, that you keep it and you short that end of that cable and insert it into a system, as you see in the picture here, that looks like it's a T, right? This piece of coax, if it's shorted at a specific frequency, will act like a notch filter. So that frequency gets trapped in this loop down here, and all of the frequencies bypass that notch filter and go through. So if you were trying to, let's say, keep 20 meters out of your radio and wanted it in another radio, you could cut a quarter wave and put it insert it in your feed line for 20 meters. Now, the thing about notch filtering with this is it's typically not very narrow banded. So if you were looking for a specific frequency, say for like a repeater, and you wanted to notch out a frequency in a repeater, then you would want maybe 1 or 2 of these in line. So 2 T pieces with 2 stubbed and shorted coaxes, but you'd also have to balance it a little bit with an LC circuit. But you can build a very high Q setup like that. And when I say high Q, if you don't know what that means, it means that band is very, very narrow. So you're looking at a small portion of that frequency within that bandwidth. When you leave them open on that stub, and I think this one is open, so you're looking at a bandpass filter for that. So at low impedance, you end up sucking in all of that signal. And if it prevents a high impedance here, it allows it to pass. Okay. So you can use an open piece to do that. And that is very high Q. So it's very narrow. So the frequency you cut it for is pretty much, you might get a little bandwidth on either side of it, but that's going to be it. Okay. For a half wave stub, act as a resonance trap. It'll offer a zero, an infinite impedance and blocks the frequency coming in to that piece. When it's shorted, what it does is it takes in all of the current for that frequency. So it acts very much like a bandpass filter, but it traps one frequency in particular. So those are three very useful tools in your systems as you're going through. Okay, so tune coax for protection. Okay, when you have a very mismatched load and you have high SWR, you end up with a standing wave. And those standing waves will develop a maximum in current and a maximum in voltage. And it depends on how the phasing in, they're typically not in the same points. So you can use a quarter wave tuned piece of coax to move that voltage or that current one way or another in a system, right? So let's say you've got high SWR and you've got your amp relay opening and closing, but you've got high current there. That's a bad thing. Same thing, high voltage at a relay is a bad thing. It can create arcing. So what you want to do is move that away from that relay. So you would put a piece of quarter wave coax that's tuned into the system and allow you to move that voltage and current away from that relay. Same thing with a half wave. We talked about it earlier being an impedance repeater. So you can move, if it's close, you can move it somewhere else in the line and put a half wave in, and there your impedance at wherever that's at repeats itself at the equipment. So it's just a way to protect sensitive components. I haven't seen it used a lot like this, but you can do it, and it works very, very well. So as a testing aid, okay, so let's say you want to measure the impedance of an antenna or calibrate your equipment, especially for, velocity factors, those kind of things. You can build a piece of coax of a known length and a known velocity factor that will allow you to do very high precision measurements without having to, if you just take a random 5-foot section of coax, you're not sure exactly what the velocity factor is. You're not sure if the velocity factor is consistent. You're not sure if the impedance is consistent across the piece of coax, because those all change. The higher end coaxes will have better control over those variables. Okay, so I've done a lot of research into coax, and I actually sat with Stefano Messi from Messi and Poloni a couple of years ago at Dayton, and we talked for 3 hours about coax. So I got a really good education on it. But their coax, the way they build their coax, their velocity factor is very, very consistent in all their cable. But if you buy just cable off Amazon, you don't know, one, you don't know who made it. Number two is you don't know what their controls were. So you can end up with some crazy stuff. That's why I always say if you're going to build something, you're going to do precise measurements, build it for yourself. Okay. So get good quality coax, good quality connectors, do the measurements, and cut your coax for what you want to do. So if you're measuring impedances in an antenna, half wave is probably the way to do it. Okay. Because it repeats that impedance. So if you're at a half wave on a, say, a 20-meter dipole, and you put a half wave in it, whatever impedance to that feed point is going to be the same at your meter. Same thing if you change it to a different antenna, maybe hung a little bit lower, you can see what the exact impedance is, because it's going to reflect whatever's there gets carried forward back to your piece of equipment. Okay? Same thing, you can get a specific piece of cable and use it for calibration of your machine. So you can calibrate your Nano VNA, you can calibrate your spectrum analyzer, you can calibrate your rig expert, all those things with proper piece of coax. Okay. So that's a very valuable tool. Again, I build my own cables for this kind of stuff. I will use the cables that come with the equipment if they're good, excuse me, good quality stuff. But if it's cheap Chinese stuff, I'm not going to use the cables. I'm going to build my own. Excuse me, I've developed a tickle in my throat with this evening, and I don't know why. Okay. So tuned coax for station improvement. So again, you can use for station improvement, it's kind of a combination of different things. You can use it to measure antenna impedance with and give you a reference. You can calibrate all your equipment. And well, wait a minute. I repeated this slide. I am so sorry. I was making changes and I did not do that correctly. So basically, this should give you the details that a random piece of coax, like a 50-foot piece of coax, is not actually random, right? So you can, if you have cheap coax or if you have a piece of coax that is a specific length to a specific frequency, right? It can change the impedance seen by your radio. Okay. It's like we said, a half wave will repeat. So if you've got a high SWR somewhere and you've got a half wave on that particular frequency, then your equipment's going to see that same thing. And some coax, it'll change the SWR, right? Very lossy coax will change your SWR. So if you use good quality coax and you cut it properly and know that it's not resonant on any of the bands that you're using, then you should be okay. Sometimes coax, if it's creating a high SWR at a frequency, your tuner will have some problems. And it can make an antenna that's very good look bad, and it can make a very bad antenna look good in regards to SWR. Okay. So you always want to try and use good tuned coax for your antenna system. Again, not necessary for most cases of using broadband antennas, but if you're using monoband antennas, it's probably a good idea to make sure that you're using coax that's properly tuned. Okay. Does that ever make sense? Do we have any questions about any of that I went over so far? No? Okay. So, how do you build a tuned piece of coax? Well, what you need to know, we talked about this earlier, was the velocity factor. You need to know the impedance of the cable, right? So if you need to know if it's a 50 ohm piece of cable or a 75 ohm piece of cable or a 93 ohm piece of cable, because they're all out there and coax has different characteristic impedances. You need to know what your desired frequency is. So if you're trying to make something for 20 meters and you want it to center the band, you're going to target 14175. You want to know the phasing angle or percentage of the wavelength you desire. So if you want a 180-degree feed line, which is a half wave, then you need to target that. Or if you need an 84-degree feed line, you need to know how to target that. And you need to know the proper formulas and equations to produce the cable that you want. What you need to have to create this, number one, you need a good piece of coax strippers. Okay. Coax strippers will make your life significantly easier than using a razor knife and trying to measure this stuff out. Now, I have, let's see, I'm right here. I have it on my desk. So for LMR 400 and RG213, I have this. I'm going to switch to the other screen so you can see this real quick. I have this tool, which is the DX Engineering made for their connectors. And you can use it with several other connectors, but it's a stripping tool. Up here on this side, you've got 3 blades that will cut the insulation, the copper braiding, the dielectric all the way down to the center core. The next set of blades cuts the outer braid and the jacket, and the final one just cuts the jacket. And you twist it onto the cable and you spin it until you feel the resistance go away, and then I always turn it back a couple times just to make sure I'm cut all the way clean through. And then on the inside, on this side, you have one single blade that's along the axis of the cable. So when you close it and you pull it off the cable, it cuts that jacket and releases everything for you. Okay. And if you squeeze it tight enough, if you've got strong hands, when you pull that cable out or pull this down, typically that first section that has the jacket, the braid, and the dielectric will all stay inside this tool, and then you just open it up and shake it a little bit and dump it in a trash can, and you're good. But a good coax stripper, this is the DX Engineering. I've got this is their higher end one for the same cable. This one, I'm not a big fan of. It's a little harder to use. They have a green one, which is made for, there it is. The green one's made for RG8X. So if you're in smaller diameter cables, they have a whole system of these things, right? If you're doing times microwave, there's a time microwave tool. But if you can afford to get one of these, get one for the cable and the connectors you're using. It'll save a bunch of time for you. It'll save your hands and prevent you from getting cut probably too. So just as an aside there, you do, let me switch back. Let's see, which one was it? It's this one. Okay. You need a measuring device. What I mean by measuring device is a tape measure, right? Because you're going to have to measure how long this cable is. I like something like this one, not the 1 inch wide ones that come, because this has got some flexibility to it. I usually put the cable and hold it in my hand and then pull out the cable and pull out the tape measure at the same time to get the right thing. If you buy good coax, a lot of times there's a footage marked on them. DX Engineering marks every 2 feet on their cable. So if you buy a piece of cable, there's a marking on that cable that will, I done hooked my meter. So you can tell how long of a piece of cable you have, and unless you're cutting to like the 1 inch mark, which I typically don't. I usually cut in like 6 inch increments. That'll help you out a whole lot. You need coax connectors, obviously, at least one at one end. You're going to need a soldering iron or crimpers or whatever you're going to put that coax connector on with. If you use messing and polony cable, you really don't have a lot. You have some soldering, you don't have a lot of crimping to do. DX Engineering, most other connectors have crimps on them. You'll need a VNA or an antenna analyzer that can look at an impedance in total, right? It can look at the Z impedance, it can look at the R and the resistivity or resistance in the cable, the true ohmic resistance, and looks at the reactance. You'll need good cable scissors and cable cutters, okay? Round cable needs to stay round. So I use a pair of actual cable cutters. They're half moon, as you can see. These are Work Pros. They're pretty good. I've got a pair of Kleins as well. I keep the Kleins in my tool bag for work, but these are the ones I use on the bench. This piece down here is a way to round the cable back out. If it gets a little too flat, you can put the cable in here and pinch it a little bit and bring it back to round. But instead of using a pair of alignment cutters or a pair of dikes, use cable cutters, purposely cable cutters. These are pretty big. You can find them a little bit smaller if you're just working with RG8X, but you'll need a good pair of those. The other thing that's really good is a small pair of side cutters. These are detail trimmers. They're good for catching those little pieces of the braid that are stubborn and don't cut real easy, but you can clean up your coax pretty easy with that. You can also use it to round off your dielectric if you need to. If you get a little meat hook or something on the dielectric, you can clean it up with that. I don't like to do that. I'd like, I try to keep it where I'm not in a situation where I'm having to deal with that. Those tools that I used earlier typically keep everything nice and clean. You can, like we talked about earlier, this is a Rig Expert. This is their newest one. This is the match unit. It's really good. Now you don't have to have one that's, you know, as tricked out as this. The AA zooms all work really well. Even the old MFJs, if you have one of those styles, the old 259s, they'll show you the Z, the X, and the Y, and you can use those. Okay. And a nano VNA, even a spectrum analyzer, any of those will do the work for you. Spectrum analyzer, you're looking at the frequency and where it drops and peaks. And nano VNA similar. This actually gives you a mathematical form of the impedance. I like it a little bit better, but you can use any of those tools. Okay. And the last thing you need to have is patience, and a lot of it. Okay. If you've ever cut tuned cables before, you have to do it a little at a time, right? You just don't hunk off a big piece of your cable, because if you do that, you can overshoot and the cable becomes too short. So you typically don't want to take big pieces. Knowing the cable that I work with, I will start at like a 1 inch piece, because I usually cut 6 inches long. And then I start to increment down from there, 1 inch piece to half-inch piece to quarter-inch piece. And then I get into eighths and sixteenths even, as I'm cutting them down to get to a zero reactance on the cable. And that's what you're shooting for, is zero reactance. You're never going to get your Z impedance to zero, because there's always going to be a little ohmic resistance there, but you want your reactance to zero. And as we know, when reactance is zero, it is resonant at the frequency you were testing for. Okay. So that's that. Now, I do have a cool little tool that I came up with some help from some friends. And this is a phasing delay line calculator. So yeah, exactly, Les. That's where you need a cable stretcher if you cut it too short. So you can go in and put your target frequency. Let's say we were looking middle of the 20-meter band, 14175, and I wanted a 90 degree quarter wave feed line. And I need a velocity factor. I'm using RG213. My velocity factor is 0.66. If I was using, let's say, RG8X, 0.78, right? It's going to give you your first cut length. So at 90 degrees at 14175 with a 78 velocity factor is going to give me 13.5365 feet. So I would probably cut this at 13 feet and 3/4 just to be sure. So 13 feet, what is that? 9 inches to be sure. My check frequency, now this is what you set your meter to when you're working with these cables. That meter, you want to have it on the check frequency. So I would set my frequency on my meter to 14.175, get the X and the R up there and see where I'm at, and proceed to start cutting the cable back till I get to that zero reactance point, and it should be somewhere around 12.98 feet, which is going to be just short of 13 feet. Okay. But you want to cut a little bit long just to be sure that you don't undercut yourself, because even doing the method I do with the tape measure, you can still be off by 1 or 2 inches, and that can, if you off by too much, it can throw you in. I also have it in metric. So if we were doing metric, if you're that kind of person, at 66 velocity factor, 90 degrees, your first cut is 3.5 meters, and your check frequency is 175, and your approximate terminator length is going to be 3.34 meters in length. Okay. Now I do phasing cables. So for a Christmas array, I'm going to do an 84 meter feed, 84 degree feed line, and I'm going to use RG213. So that gives me a 10.69 foot piece of coax. So I typically cut those right around 10 feet, 9 inches, or, if I'm just want to get it close, I get it 11 feet. And then I cut from there. My check frequency is going to be 15.188 megahertz. Okay. Anybody have any questions about this tool? Okay. If you want this tool, I'll be glad to email it to you, but you can go out to my array website, performancearrays.com. And if you go to the downloads, the tool's in there. So you can go and download this spreadsheet and you can do whatever you want with it. If you want 180 degrees, let's say we were looking at 180 degrees, right? At the velocity factor 0.66, you'd have a 6.97. So cut it at 7 meters basically. And you're going to end up with something that's going to be at 6.75. So 6.6, 6.9, 6.7 meters, and your check frequency is going to be 7.08 megahertz. Okay. If you want, and this is frequency for, this should be, X
Is
reactance
that
here.
just a question, John? Does that
Yeah.
have overcorrection? So, like, if you cut it to the length that it specifies, is it slightly longer to allow
Yeah.
for trimming?
Yeah, it
Oh,
does. It
nice,
does allow
nice.
you to trim. This length is pretty good. I like a little more margin for error because, again,
Yeah.
not not all coax is created equal.
No,
And if that
no.
velocity factor is off by a little bit, and
Mm,
I can tell you, I spent about $200 on a long piece of RG11, which is 75 ohm coax, and they gave me the spec sheet said it was 80. I think it was 82%,
mm.
and I did the
It's
first
probably
couple cuts, and I'm like, these things aren't tuning. They're too short automatically just off the first cut.
it's it's probably around 87%.
Yeah, and that
Having
was the
worked in that
issue when
industry for
I
ever,
cut.
yeah,
Yeah, I cut myself a piece of coax, a known length piece of coax, and did the math to figure it out using the meter, and it was 0.87. So,
yeah,
um,
too, yeah.
yeah, so you have to be careful of that. If you buy good quality coax, again, DX Engineering, Messi and Poloni, ABR, those guys test coax like nobody's business, right? It's all good stuff. I won't speak to the stuff you find on Amazon, or anybody else's coax, right?
The times microwave would be good.
Times if you can
Yeah.
afford Times Microwave, I can't do those prices. Um, it's expensive stuff, and Comscope, if you can afford Comscope stuff, is really good, but
Mm,
it's stupid expensive as well. And I have a direct route to Comscope because we use their fiber in their UTP cabling in my business. But even at a discounted just distributor level pricing,
it's expensive, yeah.
yeah, I can't, I don't want to go that way. It throws the cost of the system too high. So, but most of the stuff I use is going to be either ABR or DX Engineering. Right now, everything I have in house is all DX Engineering connectors and cable here. So
So is that their own brand or is that
they have it OEM'd. I'm not sure who OEMs it for them,
okay?
but
Yeah, yeah.
it is good quality stuff. I'm not sure who, I know they don't have a factory, so it's an OEM product, but the tolerance on it is very, very good.
I think
Um,
it's probably ABR because
well, no, because
Gigaparts have ABR as well, don't they?
the jacket is different than ABR. So if you
Okay,
get like a piece of ABR RG213 and you get a piece of DX Engineering 213,
different.
it's
Okay,
a different material. You
yep.
can feel it almost. And the same thing with their LMR 400 or 400 Max, and it's supposed to be ultra flex. The ultra flex
Mm.
from ABR is much more flexible. So I think they have it made by either somebody like a Comscope or a Comtran or somebody like that. That's a good quality cable house. But uh, the best one I've had with most consistent results on all their cables has been Messi and Poloni. So, you know, but again, that's expensive too. So,
What about Belden?
Belden makes really good coax. And
Super
that's
expensive.
and that might be who makes DX Engineering's cable.
Oh, maybe, yeah. Yeah.
I've got some Belden RG11 in my garage, and that stuff's really good too. I don't like the jacket on their RG11. It's outside plant jacket. And it's PE, so it's very hard to use the tools on it to cut it. You typically have to take the jacket off and then cut it because that jacket's just so tough. But I'm going to go ahead and switch over to the desk. I apologize for the audio quality, but I'm going to show you guys how to cut this stuff. So I think this is the right button. Yeah, there we go. Okay. So what I did is I cut a piece of, can you guys hear me?
Yeah, it's kind of low.
Yeah, and I apologize. It's just the mic position. I was trying to get my lapel mic to work and it wasn't working real well. So this is a cut piece, 11-foot piece of DX Engineering 213U. Okay. I've already terminated one end of it. And I will tell you guys, if you're going to do this stuff, mark it, right? I have it marked, as you can see, 84 degrees and 14.175 on the jacket. Okay. I also will use a labeler, and these rhinos and some of the brothers will print on shrink tube. So you can put a piece of shrink tube on this and label it for what it is. All my stuff comes with shrink tube labels on it. I didn't do this piece tonight because I wanted you, if you don't have a labeler, know to label these things, right? Whether you do a wraparound with tape and label it, or you write directly on the jacket, so you know what you have, because it could, if you have a box of random coax and you want a specific cable, a quarter wave or whatever, if you don't know what it is in that box, then you got to get the measurement out and start looking at it. Okay. So what we're going to do, and we'll see how this works. This thing was being a little finicky earlier. So, all right. Can you see the meter in the, okay. So frequency, I'm going to do an 84-degree feed line. So my frequency is 15,188. I'll pick that up so you can see it a little better. 15,188 on the meter. Okay. And I'm going to set that as an okay. And I'm going to go to my RX chart here. And I'm going to go okay. And I'm going to come into this and hopefully it reacts right. Yep. Okay. So you can see that blue line and the yellow line going across. I'll pick it up here in a second. So the blue line that you see is your reactance. The yellow line is your ohmic impedance for that cable. And it's centered directly on 15,188. Okay. So I can see button again. So let's see what at 15,188, I have 0.6 ohms of ohmic resistance, and I have 9.4 ohms of reactance, and it's positive. So I'm going to take a little bit off the cable. So I'm going to take this and I'm going to go ahead and cut just about a half an inch off this cable. And it's long, so I know I'm okay doing that. And I'm going to go ahead and hit the button again and let it scan through. And now my impedance reactance is 8.9. So we went from 9.2 to 8.9. So I know I have more room. So I'm going to go ahead and take a bigger piece this time. Like I said, I cut this thing about 6 inches long. So I'm going to take about an inch off. And we'll go ahead and hit it again. Okay, that took it down to 7.7. So we went from 8.9 down to 7.7. So we got a little bit of ways to go. I know it's kind of boring watching me cut coax, but again, it's about patience. Okay, that made a pretty big move there. Looking at
John,
the
could
meter.
you, just a question, could you cable TDR that?
Yes, you
To get
could.
exact, yeah,
Yeah,
to get it, like, if you, like I'm saying, if you're building, once you've done your first,
Mhm.
take a TDR measurement, and then you could just do a batch
Right. Exactly.
and watch it. Yeah.
Yep. So you're at 6.6 now. So we're taking about 1.5 ohms each time we cut it of reactance out of the system. Cut it again. Let's see where we're at now. Okay, that's another pretty good move there. Okay, we're at 5.2 now.
I had a question.
Yes, sir.
It looks like you have a connector adapter on the VNA.
On the rig expert, yeah, it comes with an end connector.
Yeah, you accounting for the length of the adapter?
Yes, I've got that zeroed out.
Okay.
So yeah, I should have said that earlier. So now we're down to 4. And there's a neat tool on this thing, which I'll show you once I get it close here. Yeah, now it's getting real close. 2.9. We're going to start cutting a little bit smaller now. So I don't think I'm trying to do this with one hand.
And the reason for 15 decimal one, what was it? 188?
188.
Is
That's
that mid band or?
yeah. So
No,
that
yeah.
is the frequency where 84 degrees at
Yes.
14175 is 90 degrees.
I'm with you.
Okay.
Yep.
Make sense?
Yep.
Yeah. It's just a math trick that makes it easier to do this stuff.
For sure.
1.4, so we're getting close now. We'll cut these things down just a little bit smaller. I don't like to cut when that meter's running. Okay, 0.9. I know kind of how much I need to take, but I don't want to take it just in case. That should be about 4.
Watch those fingers.
What size?
I said, watch those fingers.
Yeah, exactly. Yeah, it was exact. I cut that. I said it was about 0.4. It was exactly 0.4. So I need to cut just a little bit. About right there. And that should get us 0.2. Close, but no cigar. And you want to try to make this as close you can to flat. And I think we got it there. Right. Okay. So I'm going to stop this. And you can see that blue line is right on the 0. This thing is 0.0. So it is perfect match to that frequency. Now, this has a neat tool. It's got a stub tuner. So if I leave it at 15.188, which is 84 degrees, it is an equivalent of 90 degrees, or 84 degrees at 14.175. I can hit this and hit OK, and it takes a second, but it'll give me an approximation of where this is at frequency to the stub. .19 megahertz. Now it's probably 15.188 directly, but this only goes to 2 digits. You can see that 15.19. So that is a quarter wave at 15.19 or 15.188. So now what I would do is terminate that end. and I'm done. Presto changeo. I have an 84-degree feed line. Okay. Anybody have any questions about the procedure for that? That all makes
You hear
sense?
me?
Yes.
You can hear me?
Yes.
Okay. So what do you do when you're working with like a tri-band or multi-band antenna?
Well, so that's a different math problem, right? So with a tri-bander, because they're all in I don't want to say reference, but they're all multiples of each other, right? 28, 14, and 21 are all divisible by 7, right? So I would do a half wave in the middle of it, which would be 21. So I would build my half wave to feed that antenna at 21.
To try and do the best all the way through, one end to the other.
Right. So because half wave, 3/4 of a wave, or I'm sorry, half wave, full wave, and a wave and a half are all the same. They all repeat, right? Because it's all in half wave increments.
Okay.
So actually, let me think that through. Yeah. So that would work. That would work fine, right? And then if you're going to do quarter waves, then that's going to be your impedance transformer, right? So quarter wave, 3/4 wave, 5/4 wave, 7/4 wave, all those are going to be impedance match transformers. Okay, does that make sense?
Yes, very good.
Cool.
If you'd have to flip, you also have to flip your feed point on your Yagi, one
Right.
of them,
Right.
to get the phasing. Is that
Exactly
correct?
right. Yep.
Yeah.
Yep.
So it has to be mirror image, like an upside down stack. So yeah.
Exactly. Anybody else have any questions? Was this valuable to anybody?
Definitely.
Okay.
Yeah.
Cool.
Really.
Having a good time.
All right. Cool.
Absolutely.
I mean, if it wasn't clear on anything, please let me know. And if I made a mistake, because I know a couple of you guys are in here have done this a bunch, please tell me.
One
because
question I do have
Yes.
is I'm used to soldering all my coax connectors,
Mhm.
and I want to look at what it is to use the crimp fittings. If I'm working between 239 and the 400, Allen 400,
Mhm.
is there a particular number, or on these crimp tools, do they print on the
Yeah,
unit what is for?
So on the die, on this one,
Tell you part number and
it's
size
got,
of it.
so the die itself, and I'll try to bring this up. I don't know if it'll focus real well, but
Okay.
all that stuff is 213 LMR 400 RG8X is all right around 0.4 in of an inch. So this crimper is set for that 0.4, right? And if you buy a one that's for RG8X, RG6, what else is down there? RG58. They're all about point.
The 8U?
Yeah. Oh no, 8U is going to be big. 8U is 0.4.
Okay.
8X, 240, RG6, RG58. They're all about 0.221, and the crimp tool will have 0.21. And I have a set of dies in here. Bear with me a second. Let's see if I've got them here. Put my hands on them.
And the center pins are common too, aren't they, John? Is that right?
Yeah, so you
Same
will see
again.
them. I don't use center pins. I solder everything. So if I bring this piece of coax up, you'll see that's soldered.
Yes.
Right. So you solder the center pin
Right.
and you crimp the body. Right.
Right. Okay. Good.
Because they're PLs. The N types generally are crimped.
Yeah, N types are crimp. I don't
Yeah.
do a lot of N. And so
Yeah.
are BNCs. Those are crimp as well. So this is a set. This is a set of dies. It's got a couple different
Okay.
Yeah.
Sizes.
So you just buy the tool that you need
For a particular cable size.
Yeah, for the particular cable
Okay.
size. Now, if you want an all-in-one kit and you don't mind shelling out a little bit of money, I'm not
Right.
hawking for DX Engineering, but they do make some great tools. They have a a kit that has several crimpers and several dies. So you can set yourself up, and then they make I showed you the strippers. They make a whole set of these. It's about, I want to say it's like $200 or $300. Let me look real quick. Bear with me just a second. I can look it up.
That's very economical, though. If you were to buy them all separate, it would be
Yeah, I mean, if you're
double the price.
gonna tool up, right, then you want to do it right. Buy it
Once.
one time, right?
Mm.
Crimp tool.
The Greenlee.
Yeah, Greenlee's got a good set too.
Mm.
Oh,
This is a Swedish brand as well. I'm trying to think of the name of it.
It's
With a
not
no name.
Neural, is it?
Possibly, yeah.
Yeah.
They're really good. Yeah. Expensive, though. Well,
Right.
in Australian dollars, it's expensive.
Yeah. Now you in the States?
Yeah, I'm here pretty much 70% of the time, John. That's why
Okay.
I decided to. I'm in Charlotte, so I just thought I saw. I think you were on one of the podcasts, and I thought, oh, this looks like a good club. I'll wander down. So
Yeah, I was probably on with Jim the other day, maybe.
yeah, so
I'm gonna be on with Jim on Sunday if we have power again, and then I'm on Thursday and Saturday next week with the Coffee and Ham Radio guys, Ape and Chuck. So the DX Engineering two crimp connector setup. It's got the trimmers, it's got the cable cutter, it's got the crimp tool and the dies. It's $250 for the full set, and
Yeah.
you get all the dies, right? So that makes all the sense in the world for that. The stripping one with all the tools for stripping, and that gives you 4 stripping tools and 2 cable holders and a set of cable cutters. It's $300 for that kit, but well worth the price, because those things are expensive by themselves if you buy them separately. So you get the 8U, the 405, the 240, the 405, and for the end connectors and the PL 259 connectors. And you get a set of replacement blades for, it looks like, for all of them as well. So
okay. Thank you.
yeah, no worries. Glad to do it for you. I just couldn't remember the prices off the top of my head. So $500 basically would get you fully tooled up with for any piece of coax you'd want to do. Okay. You can do it off Amazon too. I mean, I've bought stuff at trade shows, and these tools, I've got a ton of them in my drawer here. I've got different ones. I typically stick with Ideal or DX Engineering for the coax stuff. Ideal usually for terminals and things like that, just because I like quality stuff and I use these all the time. I mean, I make probably coax in the last 6 months. I've probably made 300 or 400 coax cables. So, it's a lot of crimping, and you want to have good tools for that. You can't use something that's going to break after 100 crimps. So, what else can I answer for you? Anybody have any general questions?
Yeah, I just want to add a comment.
Sure.
Talk about the velocity factor. What happens is, because of construction of the cable, and especially the dielectric, it slows down the propagation of the wave. Although it doesn't change the frequency, it just slows down the propagation. There's another application where you want to slow down propagation. It's called something else, and it's right here. It's right here. It's called refraction index.
Refraction index.
The same thing. It's the same thing.
Yeah, we deal with that with fiber optics, right?
Yeah. Okay.
Yep. So if you deal with fiber optics, there's a refraction index, and you refract the light in the center core off the cladding, and it bounces back and forth within the center core. Yep. So, not that we're going to get off subject of fiber optics, but yeah. So, Yeah, velocity factor is going to be very important. You want good quality stuff, like I said, for that, if you're going to make these cables.